final lesson of our introduction to area under a curve is part D, and this might be the most difficult piece that we talk about so far. So we're going to take some time, and this might be a longer video, but we'll also take some time to look at it and review as well Monday before a quiz possibly, or coming up on Tuesday. So don't panic that I'm not here. Watch the video, work on the worksheet, do the best you can, and we'll talk about it again on Monday. Calculation of area under curves. When we start talking about calculation of area under a curve, we basically introduce it by use of what we call rectangles, because we all know how to find the area of a rectangle. So if I find the area of a rectangle, length times width, or in this case, width times height, is what we're going to work on. So we're trying to find the area of this shaded region from 1 to 4 and under that curve, okay? And what we're going to do is we're going to approximate it and eventually basically get it to be a limit. We're going to close in on it and approach it from both sides and find the area. So first of all, when I calculate upper rectangles, to calculate upper rectangles, I'm going to take the width of the bar times the height of each bar. Well, what's the width of each of these is 1. Okay, the width of each of them is 1. So that's where these ones come from. Now, what's the height? The height is actually, the height of this one is 5. Well, where did that 5 come from? 5 comes from when I put 2 into the function. So when I put 2 into the function, I put 2 into this function, 2 squared is 4 plus 1 is 5. So that's where the 5 comes from. So this is really 1 times 5, which gives me the 5. The next one is 1 times the height. When I put 3 into the function, I get 10. So this is really 1 times 10, which is 10. And the last one is 1 times 17. Okay? And that's what this represents, 1 times 17, which is 17. We add them all together, you get 32. Now, obviously, that's more because there's this extra piece above the curve that isn't really part of the area we're trying to find. So what we're finding now is we're finding an area that's more than the actual area under the curve. Well, on the next one, we do lower rectangles. So here we found the area of the upper rectangles, upper meaning it's the upper side of each of the bins, each of the bars. That's why it's called upper, because it's the greater side. On the next one, we're going to look at the lower side of each of the bars. So now we're finding still the width is 1 for each bar, but now the heights are different because I'm going to the lower edge of each of those. And obviously that amount is less than, the area we're calculating now is actually less than the actual area under the curve. So we do the same process. 1 is the width times the function. Well, 1 times 2. When I put 1 into the function, when I put this 1 for x into the function, I get 2. So 1 times 2 is 2. And then for the next one, 1 times 5 is 5, and 1 times 10 is 10. So we add those up and get 17. So right now what we know is that the area is somewhere between 32 and 17. Now, is it exactly in between? Is it the average of them? That's something we're going to work on and figure out. But right now, all we have an understanding of is that the area, the actual area, is somewhere between the area of the lower rectangles and the area of the upper rectangles. And that should be a lowercase u, not just a u. It should be a subscribed u. Okay with that? The area, the actual area under the curve is somewhere greater than the lower area, because this is lower, and somewhere less than the upper area. Well, what we continue to do is, so here we had bars that were 1 inch or 1 unit wide. Well, we can break them into half unit wide. So we break these into a bar that is half unit wide for each of these. So that's where the half comes from. Times, well, this is the 1.5 mark, so I put 1.5 into the function, and I get a value, and so on. Well, if you realize, isn't 1/2 common to all of these? So I factor out the 1/2, and then add up the terms of the function. Notice the 5, 10, 17 are still there because that's when the function's at 2, 3, 4, but they also add in 3.5, 2.5, and 1.5. Now these are the upper bounds, so these are the upper width rectangles, and we add it all, add them all up, multiply by a half, and we get this. Well, we do the same with the lower half. And we do the same with the lower half. So they're still a 1/2 inch wide, or a 1/2 unit wide, but now we're using the lower sides of the rectangle, so I put 1 in and get 2. And then I put 1.5 in. Well, I already figured out what 1.5 was. It was 13/4, 5, 20, and so on. But notice the 17's not in there because 17 would be the upper side of this rectangle. So I don't use the upper side. I use the lower side of that rectangle to make those. So then we'll add those up, multiply, and we get this area. So now we know that the area is somewhere between 20.375 is less than the actual area is less than 27.875. So we know we're zooming in on it. Before, when we did it the first time, when the rectangles were 1 unit wide, we knew it was between 32 and 17. Now we know it's between 28.75 and 23, or 20.375. So we're zooming in on it. We can continue to break it further down and zoom even closer in on what that looks like. Here I'm using 1/4 widths, and I didn't write it all out, but that's what we're using now is 1/4 widths. We can continue calculating. So as that measurement gets closer and closer to 0, as this gets closer and closer to 0, obviously if it becomes 0, we get 0 for an area. So we can't become 0, but we can get closer and closer to that small value. That leads us to the concept of an integral. And these are what we call definite integrals. And this is what the notation looks like. An area under a curve is equal to a definite integral from A to B. So this would be my lower limit, and this would be my upper bound. I'm bounded by lower and upper parts. So the area that we know has to be greater than 0, but it's between, and I plug A into the function, plug B into the function, and that's how I actually get it. So when I'm actually doing these, what we're going to be doing so far is we're going to be looking at simply using graphical evidence to do it, because we'll teach you how to do the actual integrals later based on integration, the process of integration, but we're just introducing it now. So we're going to teach it by use of graphical evidence. So what you're going to want to do for these problems when you get to this is you're going to actually want to graph these and find out what you're looking at. So for problem A, if I graph problem A, I wind up with a graph that looks something like this. Okay, it's 2x plus 1. So a slope of 2, here's the y-intercept of 1. And when I get over here to 2, there's 1. When I get over to 2, when I put 2 into that function, I get this height is 5. So this is the point 2, 5. This is the point 0, 1. And I'm finding that area. Well, do you know how to find the area under the curve from 0 to 2? So I have to find the area under this line from 0 to 2. So I'm going to try to find this area, that striped area. Well, if you know how to find the area of a trapezoid, you can easily do that. And that's what an integral is. The area is equal to the integral from 0 to 2 of 2x plus 1. Now that dx part is just a notational thing. And we'll teach you what that means when we get into the more formal calculus. Right now, we're doing introduction. But an integral is area under a curve. So can I find the area under this curve? Well, yeah, if I know how to find the area of a trapezoid. So I use the area of a trapezoid. How high is this side? That side's 1. How high is this side? 5. What's the distance here? 2. And that's really all I need, because remember, area of a trapezoid is base 1 plus base 2 divided by 2 times the height. Well, base 1 are the two parallel sides, so that would be the 1 and the 5. 1 plus 5 divided by 2 times the height is the other side, because it's perpendicular to both those sides. So this is 3 times 2, or 6. So the integral of this is simply 6. The integral of this problem is simply 6. So if we take the next problem, and let's do this one. This one seems a lot more complicated, but once you put it in a graphing calculator, what you're going to see is your graphing calculator is going to tell you this is what that looks like. And it looks like that because it's part of a circle. And it goes from, this point is 0, 1, and this point is 1, 0. And we want to find the integral from 0 to 1, so we want to find that area from 0 to 1. Well, isn't that just 1/4 of a circle? So when calculating this problem, again using graphical evidence, the area is equal to the integral from 0 to 1 of the square root of 1 minus x squared dx. But in actually calculating it, we're simply going to go 1/4 of a circle, 1/4 of a circle. And the area of a circle is pi r squared. What's the radius? Times 1 squared. So in this case, the area, the integral in other words, is 1/4 times pi, or pi over 4 square units, whatever that is, whatever units we're working on, that's the area of this integral. So it's really based on geometrical representations, and an integral simply means that's one of the applications of an integral is to find area under a curve. So it's just some notational things that we're working on, being able to understand that integrals mean area, and from there right now we're simply going to work on it using graphical representation so we can calculate it using some geometry formulas that we've worked with before. Have a great day.